Okay, so I will talk about thought experiments, and in particular, an attempt to try to make them a bit more explicit by trying to develop a way to program them in a computer, and in particular in something that could be run in a quantum computer, although that's not as important. So just to say, this is joint work with Nuria Nurgalieva, who is almost finishing her PhD at ETH Zurich and is looking for postdocs, and she's excellent, so feel free to hire her. And Simon Matis, so he was a master's student at the time, and this started as his master's project at ETH, supervised by Renato and me and Nuria. He's now doing a PhD in Cambridge in something completely different, in artificial intelligence in biology. Okay, so just to summarize what we do, and I'll run through an example. So what to do is to come up with a whole software suite where you can go and try to program your own quantum thought experiments. So you can set up like the experimental protocol, for example, that's what's here on the left, like all the steps of the protocol. You can set up how you model the brains of agents as quantum systems. I mean, if you make them small, if you make them large, you won't be able to run this in a computer. And you'll be able to like determine like, or configure what are the logical axioms that you're using, how agents combine statements, how they make inferences, and also what interpretation of quantum theory they use. Is my screen sharing paused? What picture are you looking at? I have something here saying that my screen sharing is paused. Oh yes, you're still
on the first slide.
Oh no, how do I?
Yeah, sometimes it happens. Sometimes it happens. It happened to me also.
Stop share. Resume share. Okay. Then sorry for talking so much without a physical support.
Share it again.
I share it again. Okay. I try to move this bar away. Okay, now you can see their faces, much more relatable. Okay, you can see everyone now? Yes, you can. Good. Yes. Now it's paused again. Resume share. I think when I press any key, it just stops it just pauses the screen share. Okay, give me a second. No, now it works again. Now you see everything. Now I press play and it pauses the screen share. Okay. Give me a second. Maybe I need to start it here first and now try to find Zoom again. This has never happened before. Does anyone know how to solve this?
Yeah, you could share the whole screen.
Avoid using the slide share.
Sorry?
No, you don't need to maximize.
Yeah, I suppose not. Then you just miss on the nice animations, but that's okay.
Lydia,
yeah.
If you share the whole screen, it tends to work better than if you just share a window or program.
Of course.
I don't know which.
Let's try to do this. And now this. Okay, this works. Yes, okay, very good. Good, so as I was saying, like we have the software package that you can, it's open source, you can check it. The link is here, but it's also on the website and in my abstract. So you can try it out. after I explain a little bit how it works, there are some examples there that you can go step by step, and you can like try to model your quantum thought experiments and see what goes wrong, or you can try to tweak an interpretation a little bit and see how it changes things. In theory, that's the goal. So let me give you a bit of motivation through an analogy, which is just talking about thought experiments in general. The idea of thought experiments is to test all the consequences of a given theory beyond what we can actually implement in the lab, right? The hard thing with them is try to identify what are all the assumptions that go into a thought experiment, because sometimes it's just we have all these unknown unknowns that's just from the framework that we use. We fail to identify some assumptions. So for example, in the case of Maxwell's demon, right? This idea of, oh, there's this small being that can observe the direction and velocity of every particle, and then opens a door for free in the middle of this compartment of a gas, and therefore can create these two regions, one that's hot and one that's cool, that violating the second law of thermodynamics, right? And at the time that this was formulated, there was not even this notion that information is to be stored somewhere, right? This information about these things need to be stored. And there was nothing in the theory that allowed us to even formalize this, which is why it took one of the reasons why it took so long for Landauer to come along and say, oh no, look, the demon must have a physical memory where they're actually storing all this information, right? And the same happens in quantum thought experiments. Maybe not things like Bell experiment, which is no longer a quantum thought experiment because we reached this limit, but in general, like we try to phrase it in a simple way, but there's so many implicit assumptions that are going to there that it's very hard to try to disentangle all the premises when a thought experiment leads to a contradiction, and try to see like, how can we really change this? So our modest attempt, and people who actually work on software tell me that this is very naive, but our idea is that, if you try to actually code a thought experiment, this really forces us to, one, have an explicit model of what it is an agent, for example, as a physical system evolving, like how am I modeling Maxwell's demon? How am I modeling like their encoding of information they observe, like the measurements they do, how they encode it in a memory, all these things as a quantum system, right? It also forces me to implement, or it can force us to implement all these concepts we take for granted of logical systems, like how agents update beliefs, what is considered common knowledge and how they use this, all these things, try to make them more explicit. And also when you talk about different interpretations of quantum theories, it can really force us to say, if we have to try to program what it means for an agent to use a theory, what inferences they can make, then it can make a bit more explicit what are the practical differences between different interpretations of quantum theory. And the other thing that ideally to help us is, okay, if we found a paradox in a given experimental scenario, like a beginner's friend scenario, now we can very easily just change a few things in the program to try a different physical setting, right? So that's why we have this modular approach where we have all these different components, the logic, the interpretations, the setting, how we model the physical agents, and so on, and we try to explore the consequences of this, right? Now, I mean, what my boyfriend, who was a physicist and now is a systems engineer, said is that this is super naive, because also when we coach, we have so many assumptions going to there that we'll never, in a way, we'll ever completely manage to really disentangle all these little things. But it's a first attempt. Okay, so let's start then. And just to make sure we're on the same page, let's consider for now interpretations of quantum theory, where at least at some scale there is a unitary view of the measurements, like like Mauro said before, that, for example, in the Stern-Gallach experiment, what's happening is that I'm entangling the spin degree of freedom with the position degree of freedom of the electron, or other particles, and this massive field, and that at the end we observe the position degree of freedom, right? So now one could say, well, we take this to more scales, right? So now we don't actually measure this electron that hits here, but we measure this goes through an interaction with the photon, and then the photon hits our eyes, and in the end everyone is entangled. And as everyone here knows, like the Copenhagen interpretations is about where you put the cut, right? Where you put the cut between saying, okay, I know it's an unitary evolution, but for all practical reasons, I'll assume I'll model it as a measurement, right? As a non-unitary map. And the classical example is this Wigner's friend thing, where we have two agents. Alice is here inside the lab, and she can model this spin that is in state 0 + 1. And maybe in her mind, what she's doing is a projective measurement there, and that's it. She doesn't even model her own memory as a quantum system. But someone who is from the outside and sees all of this as a quantum system evolving can model her measurements in a very simplified way as a C0 between one register in her memory and the qubit they measure, right? Of course, this is it's a big simplification, but let's just take this for granted for now. Okay, so let's give you a slightly more complicated example. So now we start having a game so that we can see how logic happens, right? So here's a setup. So Alice has this qubit R, which is in this state, a superposition of 0 and 1 with different coefficients, which for now don't really matter. So she measures it in the Z basis. And if she observes outcome 0, she prepares a second qubit S in state 0. And if she measures outcome 1, she prepares this qubit in state plus, which is 0 + 1, right? She gives this qubit to Bob, and Bob needs to measure it also in the Z basis. So far, simple experiment. Okay. So how would we model this? So now think again that we are Wigner, we are from the outside. And Wigner has this kind of Copenhagen interpretation. Is looking at all of these as evolutions of unitary quantum systems. So it sees that, well, first, we have this first register, which is qubit R. It's measured by Alice. This is a unitary evolution, for example, a C0. And then depending on the state of her memory, her experience, she'll prepare this qubit S in one of these two states, which essentially is, if your qubit S starts in state 0, she will apply a Hadamard if she saw outcome 1 and otherwise leave it alone. So how would Wigner model this? Well, say from the outside, it's a controlled Hadamard, right? Controlled on Alice's memory. She gives this to Bob. Bob measures, which is again a C0, as in from the outside. Right? Okay, now we forget this unitary view. And now let's just add a game element, which is now Bob needs to guess what Alice's outcome A was, okay? Depending on what he got. So he has all these possibilities depending on what he observes. So he observes B, which could be 0 or 1. And then he needs to guess what A was, right? And so let's think a little bit about this. So if he obtains outcome 0, that should be compatible with both the system S being state 0 or the system S being in state plus. So he cannot say anything. He cannot make any of these inferences. But if he measures 1, then he knows for sure that that system S between these two options could not have been in state 0, must have been in state plus, which means that Alice must have obtained outcome 1. So this is the only inference that Bob can make with certainty, right? So I'll give you now a classical example to keep in your mind. Some people here already heard this joke, which is that, three logicians walk into a bar and the bartender asks, does everyone want a beer? And Alice says, I don't know. And Bob thinks a little bit and says, oh, I don't know. And then Charlie says, yes, we all want a beer. And the bartender gives a beer to everyone. Right? And it's the kind of same reasoning that comes here, right? So what did Bob do? Bob observed that he didn't hear anything from Alice in that case, right? And he knows, well, if Alice didn't want a beer, then she would have said something. She should have said that, no, we don't all want a beer. But because he didn't hear anything from Alice, that's his observation. He knows that Alice wants a beer, right? So that's his conclusion. And here it's exactly the same kind of classical reasoning. It's just that the observations are not about what you hear in a bar, but are about the measurements that you perform. Okay. So later we'll see how we program like the fact that Bob reaches this conclusion. Okay, but for now we just take this classical intuition. So let's now think about how we model Bob's brain as a physical system. So we're interested in this yellow part of the circuit. And here's the idea. So he has these 4 possible inferences. So these are possible beliefs of Bob, right? And he knows that only the last one is true and all the others are false. So we'll include this. So now we expand here Bob's brain. The first line in the circuit is still the qubit he measured. The second line is still where he stores the outcome. And now we add these 4 lines, which are possible inferences that Bob could have concluded were true or false before. Okay? And we just say, look, we're going to encode for now the beliefs of Bob, this reasoning that Bob did, as the quantum state of these inferences. Okay? And then we're going to have some quantum circuit that takes the observation of Bob and takes the original beliefs of Bob and evolves this in a way that encodes logical reasoning to reach Bob's final prediction. So just think about this, that for now, imagine that Bob's, the logical system he uses, this is encoded by the type of unitary he applies. His original beliefs are encoded by the initial state of this inference qubits, which will determine later how they come about. And then all that his brain does during the experiment is like, I knew before that if I was going to observe B equals 1, then I could conclude A equals 1 and nothing otherwise. Therefore, there's going to be a circuit that's going to, take the outcome I see, take these inferences and evolve them. And then we just encode this prediction, this final prediction of, I think that A is 0, I think that A is 1 in these 2 final registers, which are what we call the prediction registers. Okay. So this is a very simplified version of just Bayesian update. Are you with me so far? If there's questions at this point, please ask, but you need to unmute yourself because I cannot read the chat while sharing screen. Okay. All right, so this is our model. So how is the experiment so far? As seen from the outside, seen from beginner. So far we don't need to model Alice's brain very much. We just model her outcome prediction. So first we have Alice's actions, which was the measurement and her state preparation of the second qubit. Right? Then we have Bob's actions, which is his measurement and this big unitary that encodes his reasoning. And now how could someone from the outside check if Bob's reasoning was correct or not. Well, he repeats this experiment many times, and every time at the end of the experiment, Wigner measures these 3 registers. So he measures Bob's prediction register, and it measures Alice's outcome, right? So that's the same as like asking Bob, okay, so what was your prediction? Did you predict that Alice would say 0? Yes or no? No. Did you predict that Alice would have gotten 1? Yes or no? Okay. And then he also goes and asks Alice, oh, what did you actually observe? Right? That's what these measurements encode. Is that clear? So if there's consistency between this, then we say, okay, Bob's reasoning is pass the test. I see that there's some things in the chat which I cannot read. So, okay. No, I can't. Okay. So we still don't know how Bob reached these inferences in the first place, right? So now let's think a little bit about this. In the case of the logicians in the bar, they could have had all this thought process before they even entered the bar, right? If they knew that the bartender was going to ask this, and they knew that Alice would go first and Bob would go second and Charlie would go last, they could think of this strategy, right? Like, if I hear them say nothing, it's because they want a beer. If Alice didn't say anything and Bob didn't say anything, and I know that I want a beer, then that's because we all want a beer. Okay? So what this means is that in practice, we all kind of run little simulations of the scenario in our head, even before we start the scenario, as long as we know what's going to happen. It's the same in all these logical puzzles when you have, people with hats or blue eyes and brown eyes that need to guess each other's eye color or hat color, or these puzzles with prisoners that need to arrange a strategy in advance that would help us solve some logical puzzle. In all of these cases, when agents are like in their minds trying to decide a strategy, they run simulations of the experiment. So here we do the same. Okay? So we say, Bob, before he even measures S, he's going to run in his head, he's going to think about the logic of it all. So for this, what does he do? He runs a small simulation, right? He needs to know, okay, if I measure this, then it means that Alice got that or not. And now what type of simulation he runs depends on his interpretation of quantum theory. That's the thing. Depends on, for example, even within an interpretation, within, for example, Neo-Copenhagen interpretations, it depends on where he puts the cuts, right? Do I model Alice as unitary, or do I model her as a macroscopic agent? So in this case, because he's interested in knowing Alice's outcome, he's going to model her as a macroscopic agent in a special case. So it means that he models her memory getting entangled with the qubits. This is the first part of the measurement. But now he's interested in these different cases of A = 0, A = 1. Right? So it just projects this stage, the joint stage so far, on what happens if Alice now were to measure her own memory and got outcome A. And then he evolves the rest of the circuit, including, for example, a small model of his own memory without the whole brain. Just to see, for example, okay, she got outcome 0, so the whole state is projected to 0, 0, R and A. Then she applies this Hadamard, so nothing happens to S. So then when I measure, I get B, and B can only be 0. That's one case. And then it says, okay, so now so now I project into A = 1, so I get state 1, 1 between R and A. I evolve the circuit, and then when I measure my outcome memory at the end, I could get outcome 0 with probability 1/2 or 1 with probability 1/2. And from this, so now he has these tables of like possible values of B and A, possible combination of B and A. And from this, it just makes the classical inference like we did before when we were thinking ourselves about the experiment. That, okay, the only valid thing, the only thing I can say for sure is that if B equals 1, then A equals 0. So then he goes back and he starts before. Now, when he goes into the actual experiment, he sets his brain kind of inference registers to this value, meaning that 1 is the only one he believes to be true with certainty. Okay. So how do we do this in the software? So by the way, the software is out, but the paper is not out. But to prove that the paper is almost out, I copy extracts of the paper here. So in the software, what we have to do is to define every step of the protocol. Like now Alice goes and measures his state. Now she prepares that. At time 3, she does that. And what are all the agents and systems that are involved in each action? And then the software automatically determines like how many qubits they have to allocate to each agent. You also include in the protocol, at this time, Bob will need to reason about Alice. So this is a part of the physical experimental protocol. Right? And then what we need to do is to initialize these inference qubits for that encode Bob's beliefs. And for this, is like we put ourselves in the place of Bob, and the software automatically runs these simulations, right? And what goes into these simulations is what classical logical abstract logic Bob uses, and what interpretation of quantum theory Bob uses as well. In this case, for most interpretations, you get the same, but later on you'll see it's a bit different. And then again, we have the inference qubits of all agents. We run the protocol, and it outputs the predictions of all the agents. So, okay, yes. So again, the ingredients that go into here is that how we define a quantum interpretation is by how agents make the simulations, right? Do they simulate things as a unitary? Do they simulate it as a collapse, one or the other? And you know, at the moment, this is still a bit clumsy. And what it does is each interpretation defines an inference function, which is forward, meaning I'm thinking about experiments that will happen after my observation, or backward. So I'll think about something that happened before my observation. Right? But then the other thing is that the other ingredient is logical systems. So can we combine, for example, what this means here in model logic is, okay, I means agent I knows. If agent I knows that A implies B and that B implies C, can we take for granted that they know that A implies C, right? And is this also true across agents, right? Do they model each other as, you know, logical reasoning people or individuals, let's say, to be more inclusive. So which means here is like, if agent I, so Isabel, if Isabel knows that A equals B, and Isabel knows that Joe knows that B equals C, can we take for granted then that Isabel knows that B equals C? So she knows that Joe knows this. Does she trust Joe to be a rational agent to the extent that she can just absorb this knowledge, right? So this is in the Farag-Arena experiment, which is the one where we're going to lead up to. It's one of the assumptions that can go wrong and that people can criticize. Okay. So now, so far this was a very simple thought experiment. To look for something a bit more interesting, we can complicate it a little bit. Can someone tell me how much time I have left?
You have lots of time.
Lots of time. Okay. All right. Okay, so we're going to complicate the experiment. So we put Alice and Bob inside closed labs, and now we have these meta agents from the outside, which we call Ursula and Wigner, which will do things to them. So first, what you do is Alice will reverse whatever Ursula will reverse whatever Alice did before, whatever unitary reasoning circuit Alice did. And then she'll go and measure part of Alice's lab. And now we know what this means in practice, because we know that we model Alice's reasoning as a unitary circuit. So Ursula just needs to go and reverse it. She's going to measure Alice's lab in a special basis, which is this basis. There's two states missing, but they never occur. And this is just building up to the Farrow-Guarani experiment. You could put other things here. Yeah. And then Ursula, this is the interesting part. Ursula, given the outcome that she observes, she will try to guess what Bob's prediction was before. So let me draw this as a circuit now, first without the brains, in a lot of detail. So from the outside, even from Ursula's perspective, what happened was we have Alice's actions first. So Alice applied the C0, then applied this control Hadamard on S. And we can give Alice a brain, why not? We don't know what the initial state of the brain is because we don't know what Alice is thinking about, but we know that she'll make some predictions and she has some beliefs. And we know that she'll apply some unitary. Then comes Bob. Bob will measure this S qubit, which is again C0. And again, he does some reasoning based on his initial belief, which here is still called inference. We'll change that. And he'll make some predictions, right? And then what does Ursula do? Well, she just comes and undoes this unitary that Alice applied. That's what it means. Like, she doesn't even reverse Alice's measurement itself. She just reverses the reasoning. And she then measures R and A, so this part of Alice's brain and lab in this special basis. So this is the view, like from Alice's perspective, of what's happening here. Okay. So she's gonna remember that Ursula's job is to try to simulate what happens, what Bob's prediction is, right? So then she's gonna have to run a couple of simulations. So this now is just like in the 3 beer example. So remember there, for Charlie to try to guess what's actually in Alice and Bob's minds, first he needs to put himself in Bob's position and think, well, I know that Bob thinks that Alice wants a beer, otherwise he would have said no. And I know also that Bob himself wants a beer, otherwise he would have said no. And in order to do this is because Charlie really needs to think about, he needs to put himself in Bob's place and run the simulation as if he was Bob. So that's what Ursula will do. Okay. So first she runs the same simulation as we saw before, Bob's simulation of Alice, to get this inference that if Bob observes 1, then Alice observed 1. That's his prediction. Right? So we put it here, note here that I already initialized here Bob's inferences qubits. And now Ursula can just run a simulation of all the circuit up to now. She doesn't need to know what Alice's beliefs were, because whatever unitary Alice applied, she will just undo it, right? So in Ursula's second simulation, she just applies the identity matrix there. She runs the whole circuit up to now, and then she does exactly what we saw a few slides ago. She measures the simulated Bob prediction registers, and she measures the simulated Alice's outcome measurements, and she looks at correlations between these things, right? So then she gets this table. And she concludes, and this is because of the way we built this quantum state, and you can run the circuit if you want, but that the only thing that is true, true for sure, is that I said something wrong. Sorry, Ursula does not. Yeah. Ursula makes 2 measurements in this simulation, one of the Bob's prediction registers and one of her own outcome register at the end. Good. Good. And then, so the only inference that is valid, that is always valid with certainty, is this one, that if Ursula gets this outcome that we called okay, then she can conclude for sure that prediction had a 1 there. Okay, I will not derive this. So this is one of the things Ursula could do, and it's okay. Let me show you the other option. So the other option, again, she already simulated Bob's brain, so she knows what Bob's inference qubits are. To run a much smaller simulation where she will not simulate the whole unitary of U Bob. She just simulates up to Bob's outcome register and measures it directly. So here, the only thing that she concludes is that if Ursula is okay, then the simulated Bob saw outcome 1 with certainty. And then she goes and combines this with the other inference that she knows from previous simulation she ran a long time ago, which is that if Bob's is 1, I put myself in Bob's shoes and I know if Bob's is 1, then he thinks that Alice saw 1 as well. Right? And then I combine these 2 things, these 2 classical inferences just through normal classical logic. So we have 2 options here. They're very different in that in this one, it looks like we need more classical axioms. So we need Ursula to be able to combine these statements by different agents. But on the other hand, it's much easier to compute, right? You need way fewer qubits than in this case. In this case, Ursula makes a statement about Bob's prediction. In this case, she makes an indirect statement about directly about Alice's outcome. But the conclusion is it's going to be the same. Like if Ursula says okay, she concludes that Bob had predicted that Alice had obtained 1. Good. And now the way this whole experiment goes on is to add one more agent, Wigner. We'll do exactly the same to Bob's lab. So we'll undo Bob's reasoning and then measure in this funny basis. But then now we finally give Alice something to do. We give her a brain and we say that, well, back in the day, before she even gave this qubit to Bob, she tried to guess what the outcome of Wigner's measurement would be. So let me just show you the whole circuit. So this is, it's actually quite simple. So it's what we had before, and now Wigner comes along and does Bob's reasoning and just measures S and B in this basis. This again is the unitary view as seen from Ursula and Wigner. So now what's missing here for, Wigner and Ursula to make some inferences is that they need to initialize Alice's brain, right? So then they need to put themselves in Alice's place and think what simulation would Alice run, right? And now here we assume it's common knowledge. Everybody knows which interpretation of quantum theory Alice is using. And because of this, they say, okay, maybe Alice's simplest simulation is just the following. So she can model the unitary entanglement of herself with this qubit, but then says, okay, now I project in one of the outcomes because, I'm a classical agent. I see one of these 2 outcomes and I'm interested in what statements I can make when I see one of the outcomes. Then she evolves, her actions on S, Bob's measurement. She doesn't need to know Bob's brain state or Bob's exact unitary. So all she needs to know is that Wigner will undo this, right? Okay, and then she just, again, models Wigner's measurement. And she just now compares the measurement statistics of this experiment that has 2 measurements. And again, the only thing that's certain in this case is that if Alice is outcome 1, then Wigner will always see outcome fail. Good. Now, the special thing about this experiment Okay, so now Wigner and Ursula know this, so they can initialize Alice's brain and Bob's brain, everything. Yeah? And the special thing about this thought experiment is that there is some finite probability that Ursula and Wigner actually get okay. But in this case, they conclude through this chain of reasoning that Alice back in the day had predicted that Wigner would get fail with probability 1. That's the original paradox that Daniela Frauchiger and Renate Renner found, which I have not proved to you because you can watch one of the 50 other talks I've given about this experiment. So the nice thing here is that we can observe by modeling their brains explicitly and really saying what goes into making a prediction, what kind of simulations they make, we can really see the information flow throughout the circuit. Right? So for example, if we were to model Ursula's actions all unitarily with her brain as well, then you'd see that at the end, there's a physical register that can be measured at the end, which is correlated with everything that happened before, and which really encodes the fact that Ursula knows that Bob predicted this, that Alice had predicted that Wigner would get fail. Right. So what are the good news is that once you specify for an interpretation of quantum theory how this inference, how agents make these simulations, then the whole thing is very easy and very modular to code. So there's some examples that you can check on the software. Let me see. There they are. Right. So then you go into the software, you set up the experiment protocol, you tell them what your interpretations are, which means like what simulations agents make to make predictions, what logical axioms you have, and of course you can tweak how we model agents' brains. This was a very simplistic view where we only cared about deterministic statements and not about, for example, actual Bayesian updates of finite probabilities. Good, and then the software spits out if there's an inconsistency or not between the statements of different agents. And that's it, right? So for example, if you repeated this whole experiment, but not all the agents use collapse interpretations, then you don't find this contradiction between Alice's statement and Bob's statement. And yeah, and again, the nice thing is that you can just once you set all of this, and if you were to model Ursula and Wigner also as quantum systems, at the end of the day, you just need to measure their inference qubits, so the belief qubits of the initial state for everyone, to know if there is a contradiction or not. Okay. So this is the same as before the 3 logicians enter the bar. You get each of them in the room separately and ask them, okay, tell me your reasoning. What do you think is going to happen? And then comparing notes about all these things. Right? This would be the equivalent of, okay, I ran all these restricted simulations of all the agents. Now I have this big quantum circuit, but I just go and ask each agent at the beginning what they think is going to happen. So I just go and look at their beliefs. And see if there's a classical contradiction there or not. Or I can actually run the whole experiment and measure at the end what their predictions were, and if there is a trace of a contradiction there or not. Okay, so we think that in principle, now we come to this slide of so many issues. So in principle, I'm convinced that this is a very nice approach to treat things. In practice, there's just so many issues. So we avoid at least one big issue, which is this issue of recurrence, right? When we started, we thought, oh, maybe we'll have to have agents simulate their own brains. And if they do this enough times, there's just this recurrence problem that their memories cannot be big enough to do this. But as we saw, at least in this case, at least in this interpretation of quantum theory, the simulations they run are actually quite small, much smaller than the actual whole experiment, and much smaller than the actual brains. Yeah? So that's not so bad. I suspect that if we had, I don't know, a more maybe truly many worlds interpretation of quantum theory, and you try to encode this, then we probably would run into this recursion issues where you know the size of the thing you're trying to simulate is larger than your brain, so we could never encode that. Right, we could never have the model all of Bob, not just Bob during the experiment, like all of Bob over time, including his brain running his simulations and all of this as a circuit of finite size. Yes. So obviously, we say that we'd like for people to go and try different experimental settings and different interpretations of quantum theory and run this and see if they find contradictions, and then they can tweak a little bit the interpretations or the experiment or the logical axioms and see what happens. And we even give some very, very simple kind of sanity checks with simple settings that your new theory of quantum mechanics, your new interpretation must pass this test. For example, I don't know, if Alice and Bob measure a Bell stage, they should guess that the other person gets the same outcome. For example, they should get these correlations. Right. However, I mean, the software is still in a very clumsy state, and I think we will we'll publish it as it is, because there's no point in developing it further if there's interest from the community, which is why I'm giving this talk. For example, the way we encode each interpretations, it's done now in a very ad hoc way. We just have collapse theories and Copenhagen theories with different cuts. But for example, it would be nice to encode Bohmian mechanics or different types of many worlds, for example, there. And we don't know exactly how to do this. The other thing is like this thing I said at the beginning. Even we try to be as general as possible, but we always work within a certain framework, right? Even if we try to find a modular way to combine logical axioms, there's already some things encoded there by default that you could always come with stranger logical axioms such that we'd have to rewrite the whole code. I don't know, for example, what's a good example? We use mathematical packages in Python that take for granted that sum works in a certain way, right? And if now your sum of two numbers works in a certain way, and if you come with a logical system that changes this, then it's not as modular as I'd like to think. It's not just something you can tweak in one place in the program. You'd actually have to go and change it everywhere. This is like in Maxwell's demon case, right? That there's things that we're not even questioning and that we don't even know that we're not questioning. The other very valid criticism one can make is that, maybe in these very simple models, when Alice is just a couple of qubits, she does not have a subjective experience of seeing just one outcome or the other. Right? We don't know this. Right? Maybe in any regime where Alice has a subjective experience of seeing one outcome or the other, then there is some other fundamental problem that forbids them from doing all these simulations and tackling the problem in this way. And we don't know, and we don't even know if this software is something that would allow us to test this. I think not. Yeah, obviously, if we try to make the system a little bit more complicated, add more steps or more agents, you very quickly reach a limit where you can't run this in normal computers. And we don't have quantum computers to run this. Right, so here you have, I don't know, maybe 10 or 12 qubits, which is just about what we can simulate classically, and also quantumly, to be honest. Yes, there's things that we have not done yet, and there's many ways on how to model it, like, for example, generalizing this for finite probability beliefs and how to update them, that we've not yet done. But for all these things, the good news is that the program is open source, so you can go to GitHub, and if you're so inclined, fork it and expand it, and we'd be very happy to hear about this. So the conclusion is just, look, this is our attempt to try to bring some systematization to all this thought experiments and logical problems and multi-agent paradoxes in quantum theory. And we hope you try and let us know if you find it useful. So,
Thank you, Lydia.
I think someone is trying to say something. I can't. Thanks.
Questions?
Yeah.
Matt.
Hi, Lydia. So have you found any interesting new paradoxes using this software that we didn't know before for playing with it?
No, because honestly, we've not played with it very much. So no, but not because we tried. So we tried to make sure it works in the setting and a few other useful settings. Oh, someone should mute themselves. Maybe the room.
Sorry, what's happening?
Someone should mute themselves. There's this echo again.
It's just a room. Just a room. So.
I might be okay. Right. So we haven't found it because so far we've been focusing on making sure the software does the right thing and writing the manuscript in a way that's accessible and having these tutorial examples and so on. But we've not explored much of other settings. I mean, we have some theoretical results on why many settings would not be interesting, but no, we have not explored it. So this is open. Now I hear nothing.
Yeah, the room had got muted, but there was one person in the room who had their computer unmuted. I think that was causing the echo. Hopefully they fixed it.
Okay, so you should be able to hear us now. Lydia, do you have...
Yes.
Does it sound bad or sound okay?
It's okay. It's okay.
Okay. Go ahead, Johannes.
Yeah, it's just a minor question. I was wondering, since you have that program anyway, you could kind of think about defining what an interesting thought experiment is and just let it run and search, like generate all sorts of inputs and see if something interesting pops up. I mean, some other people are doing that, right? So, but anyway, yeah. Have you thought about that?
Yes. I mean, this is one of these exploratory things we'd like to do later on.
Yeah.
Once this paper is out. I worry that we'd run into computational complexity issues very quickly, maybe before things get interesting, but there's hope.
Yeah, thanks.
I mean, the other thing what we try to do is to really change the base theory completely. So for example, instead of quantum theory, you could have box code. But for this, we programmed everything in a quantum programming language, which takes, for example, the Born rule for granted, Project Q. So we'd have to, start from scratch again. Some of the things at least.
Okay, maybe I'll throw a question in as well. I preface this by saying that while I'm familiar with the Wigner's-Friend thought experiment, I'm not so familiar with the extended Wigner's-Friend thought experiment. So this might be a little bit naive, but so I'm interested in, sort of what was the motivation for building the software. And you mentioned at one point, put the assumptions of your interpretation in, see if there's a kind of a contradiction in the output. And that might be sort of one of the motivations for this. If I'm just looking at the Wigner's-Friend thought experiment, it looks like I can just take my assumptions of my interpretation and just figure out in a few lines what the output is. There doesn't seem to be too much of a problem just with the Wigner's-Friend thought experiment, figuring out what the latest state of the overall system is within the initial state. So it looks like when we move to the extended Wigner's-Friend thought experiment, there's sort of something more conceptually difficult that's not there in the original Wigner's-Friend thought experiment that might lead you to think, hey, some interpretations might wind up with a contradiction. And I was sort of curious just to get your thoughts on why that
Right,
is.
right. So if you don't model brains, if you have just, let me try to find it. If you don't model brains at all, you can do the, so forget the brain unitaries here. You can do the computation also quite quickly, like in 10 minutes or so, to find the contradictions. The problem is that then there's so many assumptions going there. Like, for example, that Ursula can combine her knowledge about Bob's outcome and Bob's knowledge, given his outcome about Alice's prediction and Alice's outcome and Alice's prediction of Wigner's outcome. Like this kind of things that yeah, what we'd hope is that by making it a program, we could make it a bit more modular and try to change it little by little. It's not like in this particular setting, it's impossible to calculate it analytically. It's actually quite simple. But yeah, I mean, you also need to think about, oh, do I care about what Alice's prediction was at a time, a long time ago, with this prediction that later was erased by Ursula? Do I care about the prediction that is no longer there? What is the, yeah. I mean, yeah, that's about what goes into your logical system, right? When do you say that there's a contradiction? If there's a contradiction between something you observe now and the prediction that no longer exists, maybe you don't think this is a problem.
Well, yeah, so in this picture you have like the brain, like you write down this, the protocol, and I think step 3 says something like A reasons about B. And I'm wondering, like, how important is it really for the reasoning to kind of happen during the experiment? Can these agents not just perform all this reasoning before the experiment really begins, and then just kind of have an apparatus which, you know, ballistically responds to inputs? And...
Yeah. I mean, that's exactly what happens here, right? So when you run all the simulations, what you're doing, just like setting their initial beliefs about what's going to happen, and then all this unitary that's running is like you said, like this ballistic evolution of just combining these beliefs with what they actually observe in practice. But again, depending on what you consider to be a contradiction in your, you know, in your physical theory, maybe you could say that, you know, if they believe different things, that's not a problem yet. It's only a problem if these things are later observed by, if we still have a physical trace of these predictions at the end of the experiment, for example. Does that make sense?
So David Chalmers?
Yeah, just to re-ask a version of Kelvin's question. I think that Kelvin's question was about interpretations of quantum mechanics. And I guess, Kelvin, you were saying that, well, we basically know what happens. For every standard interpretation of quantum mechanics, we know what happens at Wigner's friend. We don't need software to tell us the answer to that. And then the thought was, well, you might think that for every standard interpretation of quantum mechanics, we can also figure out fairly easily what's going to happen in the extended Wigner friends thought experiment. So then the question is, well, okay, what is the extra thing the software is giving us that, you know, we kind of couldn't have done on our own? And maybe there's two different answers there. One is, oh no, this is what Kelvin suggests. Maybe there's an extra complexity in extended Wigner friend thought experiments that make it hard to figure out what standard interpretation should say. Well, the other thing, which I was thinking was part of what's going on in some of this literature is, well, sure, when you restrict yourself to the 3 or 4 standard interpretations of quantum mechanics, we know exactly what will happen in Wigner's friend and so on. But there's actually this whole space of possible interpretations out there that we can explore that go beyond the standard 3 or 4 interpretations. And this helps us analyze that whole space and what's going on with those. Do you see this?
Yes.
as being closer to the second or closer to the first motivation?
I mean, maybe the more the more pure reason we wanted to do this is for the second reason, right? That, maybe there are more interpretations that if I change something here, but now I want to be able to quickly test if this interpretation just makes ridiculous other predictions in simple settings. So, everything a computer can do, you can do, right? This is never in question, but the computer is just much faster. So here in this case, for example, there's, even with just Copenhagen interpretations, there's so many options about where agents can put the cut between what they consider quantum systems and where they put the cut to, okay, now there's a macroscopic non-unitary evolution. That is just much faster to test it here. But again, like you say, if you want to test just something like, oh, I changed the Born rule a little bit, or I change, I changed something in a consequence of an interpretation of quantum theory a little bit, what will happen? Then again, maybe you could do it analytically. Maybe this gives us a quicker way to check this.
Okay, that makes sense. So yeah, we're really exploring the space of possible interpretations here.
And the other thing is that it really forces you to say, what's an interpretation of a quantum theory, right? What's many worlds? What does it mean? I'm in a superposition of all these things. What does it mean in practice? Now, if now I, given my experience, want to make a prediction, how do I encode this? And I'd be curious to see if we propose this to 10 different many worlders, how many different implementations we'll get. Like one of the things that after the original experiment, this extended Wigner-Friend experiment was proposed, Renato spent, I don't know, maybe 6 months almost exclusively replying to emails from angry people who I mean, and rightly so to some extent, right? Saying, oh, maybe my interpretation is not covered by this because of X, or maybe you're not allowed to use this logical axiom here. And this would just force us to make all these things more explicit and more modular and test really who's right or not.
Time for one more. Yeah, I just wanted to, I mean, it's basically in the room anyway, but so a funny idea, which probably you have already, is like other than other groups which are kind of trying to look for interesting theorems, you could look for interesting interpretations, Like you basically try and parse the space of interpretation systematically and try to define what you'd like to have. Maybe there's something.
Yes. Yeah.
Not sure.
Yeah. So for this, we need to really develop this much more. We need to have a more systematic way of like mapping, of just parameterizing interpretations, right? So that then we have a space of interpretations that we can explore. Which right now we don't have this, right? We just have 2 or 3 ad hoc interpretations now they're implemented. But yes.
Related to that, I was just wondering, so I'm going to make use of that a little bit in my talk too. So that's maybe you shouldn't ask, like in case it's wrong. But so like this. So I mean, obviously you can only represent the formalism of an interpretation, right? So you can obviously only say, here's how the quantum evolution changes, and here's how the outcomes are determined. But like, would you agree that, or would you assume that there's a one-to-one mapping between interpretations and formalism?
Right. That's nice. Hey.
Please say yes.
I think that even interpretation of quantum theories, like some versions of many worlds, they don't say anything about individual perspectives,
right?
Right. That just say something about the global evolution.
Yeah. So, but usually, like the major interpretations, they take the quantum textbook formalism and then they leave something away, put in new things, add new.
Yes. Right. Yes. Yeah.
Then, so this is part of this is the main sort of work, and then the reason they do it is because it's supposed to help with conceptual and metaphysical clarity. And so in a sense, like I think it's very like in a sense, when we know the map, we can pick out the interpretation, not by necessity, but by contingency. Like, for example, like all the collapse models differ slightly in their collapse term.
Mm-hmm. Yeah. So actually, let me give you maybe a specific example. Yes, I suppose there's something between Copenhagen and the collapse theory, where
Collapse theory, do you mean?
So for example, so here would be a way to characterize it. Like, well, Alice thinks that when Bob does a measurement, what happens is not a C0, but it's also not a projective measurement. It's some other transformation somewhere in between, right? So the way you program this is to just, in Alice's simulation, you just replace the C0 with something else, with this operator, which might or not be a quantum operator, right? This would be one way to map a different interpretation to a different implementation here. And to answer your question, like, I think what all the interpretations of quantum theory have in common is not like the global formalism of quantum mechanics, but it's they agree on the formalism on the maths for a certain regime, right? So for example, for the microscopic regime. And then they differ wildly when you start putting in microscopic agents. Mostly, I think. So I think that forcing them to tell me, okay, then how does an agent apply this interpretation, apply this physical theory to reason about what's going on in the rest of the experiment? Maybe this would help us highlight what interpretations are just semantically different and not semantic, are just different in flavor, but actually correspond to the same, for example, the same simulations, the same way an agent uses a theory, and which ones don't. If that makes sense. So for example, there could be many versions of many worlds that would result on agents employing them in the same way, but some that result in different types of maps here. And
Thanks so much. Yeah.
Yeah, and the key place where we'd see this is how do they model each other's measurements? I think this would be one place to start parameterizing different interpretations.